Okay, students, so this video is going to go over how to work problems with a KB value. So it's a very similar process as what we were doing with the KA. It's just a little bit trickier to write the reaction because it's harder to see that OH ion forming. So again, anytime it mentions a KB, it means you're going to have to do a rice table. So let's go ahead and set up our rice table. Now with bases, this is ammonia, so we'll have ammonia here. With bases, when you write the reaction, you're going to want to write a water molecule also, and this is going to help us to figure out what our products are. So remember, this is your base. That means the water is acting as an acid, so one of those hydrogens from the water is going to join the base. So it's going to add a hydrogen to your base over here on the product side, and then that means you're left with a hydroxide ion over here. Now the water is a liquid, so it does not show up in our equilibrium expression. We've got 0.15 molar solution here. We have no products to start with. We are losing some reactant. We are gaining some product. So that's why these are plus X's over here. And then we combine those two for our equilibrium row. Don't forget, I want you to write out your KB expression without any numbers. So KB is equal to the concentrations of your products, so those ions on the top, divided by the concentration of your reactant. And we just put the ammonia down here because water is a pure liquid. So now we can go ahead and plug those values into our equilibrium expression. So we have 1.8 times 10 to the negative fifth equals x times x, so x squared on the top, over 0.15 minus x. Because our x's are not raised to the same power, we can go ahead and make that minus x down here negligible, and we can go ahead and solve for x. So we have 1.8 times 10 to the negative 5 times 0.15. That's going to give us 2.7 times 10 to the negative 6 equals x squared. So then we're going to square root both sides of this so that we can get x by itself. So we square root that answer. That's going to give us 0.0016. Now in this case, because we have hydroxide, X is giving us the hydroxide ion concentration. So if it's asking us to find the pH, we want to keep that in mind, that it is the hydroxide ion concentration. So we can still take the negative log of that value. But just remember, because this is hydroxide, this is not going to give us the pH, it's going to give us the POH. So negative log of that is 2.78. And remember, this is the POH. So to get from POH to pH, we subtract from 14. And our pH is going to be 11.22. We want those two numbers after the decimal point for sig figs. That would be my answer, my pH. Okay? Let's take a look at this next question. Calculate the hydroxide ion concentration of a 1 molar solution of methylamine. I can't remember what methylamine is. All right, look it up. Okay, so you have CH3, NH2. Sorry about that. CH3, NH2. And we have KB, so that's a base. So with bases, we want to add that water so we can see how to make the products. Remember, one of these hydrogens is going to join over here on our base. So we would have CH3, NH3 plus, and we're left with hydroxide ions over here. So we have a concentration of 1 molar for our methylamine, nothing over here for our products. And remember that water is a pure liquid, so it would not pop up in the equilibrium expression. So we've got minus x plus x plus x. 1.0 minus x over here, x and x. So we write our Kb expression without any numbers, concentration of CH3, NH3, times the concentration of OH minus, divided by the concentration of CH3, NH2. So we can go ahead and plug our values in. So we have 4.38 times 10 to the negative 4 equals x times x, so x squared, over 1.0 minus x. Since the x's are not raised to the same power, that minus x is negligible. So that means 4.38 times 10 to the negative 4 is equal to x squared. When we multiply that by 1, we go ahead and take the square root of both of those. So square root of 4.38, second e negative 4, is going to be 0.021. 0.021. So we want 2 sig figs. And it's asking us for the hydroxide ion concentration. Hydroxide is equal to X. So this is our answer right here. We don't have to do anything else to this one. Okay, let's take a look at example 33. Calculate the Ka value of a 0.075 molar acetic acid that has a pH of 5.20. So this one's a little bit different because we're trying to solve for the Ka value. It says Ka, so I'm going to make a little rice table here for a second. And acetic acid is HC2H3O2. When it ionizes, it makes H plus because it's an acid, and then the polyatomic anion of acetate. We have a 0.075 molar solution. We start with no products as per usual. And then I'm going to go ahead and just fill out my equilibrium row here. Now, when I write out my equilibrium expression without any numbers, my Ka is equal to the concentration of H plus times the concentration of C2H3O2 minus divided by the concentration of the acetic acid. Now, the problem you get here is that we have two unknowns, basically. We have our X's here, and we have our Ka. Those are all unknowns. Well, it gave us a valuable piece of information in the question. It says that our pH is 5.20. So if I do 10 to the negative 5.20, that's going to give me my hydrogen ion concentration. So let me do that. 10 to the negative 5.2. So that means I have 6.3 times 10 to the negative 6. So since my hydrogen ion concentration is equal to X, I know that this is my X value, okay? So when I do the 10 to the negative pH, I'm getting my hydrogen ion concentration that is equal to X. So when I plug everything in to solve for Ka, I basically have 6.3 times 10 to the negative 6 squared, because I'm going to have X times X. I'm going to divide this by 0.075 minus my 6.3 times 10 to the negative 6. And it doesn't really make much of a difference because of sig figs. So I'm going to take my X value, my 6.3 times 10 to the negative 6, and I'm going to square that. And I'm going to divide it by my 0.075. This is going to give me my Ka for this acetic acid sample, and it's going to be 5.3 times 10 to the negative 10. Okay. Let's look at example 34. we have a 0.25 molar solution of a weak acid that is 4.70% ionized at equilibrium. What is its pH and pOH? So we know that this is our initial concentration right here. And we know that this is 4.70% ionized. So remember, the percent ionization is going to be equal to the concentration of the hydrogen ions divided by the initial concentration of our acid. So I'm going to just put initial concentration of our acid here. We don't know what acid it is because it just says a weak acid. Now, the difference here with what we were doing with our pH calculations of a strong acid, we can't just use this 0.25 molar and take a negative log of that because it's not ionized completely. So we have to use the fact that it is 4.70%, 4.70% ionized to help us to solve for this. So we're going to be looking for our H plus concentration. That's what we're going to solve for. That's our X. And our initial concentration was given to us in the problem, 0.250 molar times 100. So we're going to take that percentage, 4.7, and we're going to divide it by 100 to get it into decimal form. And so that should be 0.047 equals our H plus divided by 0.250. So then we can just multiply that decimal point by 0.250 to get our H plus concentration. And that is going to be 0.0118. So then once I get my hydrogen ion concentration, in order to find my pH and pOH, I can first take a negative log of 0.0118. And because this is a weak acid, this is going to give me my pH because that's hydrogen ion concentration. So my pH with 3 sig figs is going to be 1.930. My pOH, so I'm going to subtract this from 14 to get my answer. My pOH is going to be 12.070. So we just had to do a little backwards work there. Okay, so what I want you to do is I want you to do the practice on pages 16 and 17 and check your answer key against the one, or check your answers against the key in Schoology to see how you're doing. And let me know if you guys have any questions solving these problems. Have a good day.